So the problem of multi-model ensemble analysis is how do we take multiple climate models, an ensemble of climate models, as they usually refer to it, and combine them together to give us some sort of prediction that looks relatively close to what actually occurred. So at the very macroscopic level, where we're just taking something very aggregate like the global mean surface temperature, this problem is relatively straightforward. The way people often approach it is you just take an average and just say that's going to be good enough. You may look at a weighted average. You may look at an average that's weighted by how correlated the models are with the truth. You may look at how correlated they are with each other to try to reduce the bias. But when you start moving away from the very macroscopic and you want to get an idea of sort of the spatial variability as projected by each of these models, then you need to look at the output as these models produce it. And so what these models produce is not just a macroscopic summary. They're actually solving this differential equation around the entire globe. And so what you get is actually a discretized field prediction for the whole Earth. So at the whole Earth, we have some projection of what the, in this case, temperature may look like. And each one of these models is, of course, going to give us something that looks a little bit different, but hopefully there is some consistency there. And ideally, we'd like to use this because this would give us a lot more information. If we could somehow take this ensemble, which I've just represented by essentially this little bag or box of models, and somehow just smash them all together into one nice prediction, then that would be great because that would tell us about different local effects. We could look at local trends, and we could get a lot more information than just something very global would tell us. But this introduces a lot of problems. So for one, the models are not even natively run on the same grid. So they choose different mesh sizes that you're going to approximate your equations with. And so what that means is whenever you try to resize these to a common grid, you're going to incur some sort of bias. Or in the case where you essentially make the grid more coarse, you can lose quite a bit of information. When you start wanting to think about, well, how do these models relate to it? You can just take the naive average. You can take the naive average, of course. But if you want to do something a little more sophisticated, you have to start thinking about how do these models relate to each other? How do they relate to the actual observed data? And this problem actually blows up very quickly because you're no longer just saying, how does one point relate to another? Now we're saying, how does a whole field relate to another? And how does that happen at a local level? And how do we account for that some parts of the field can affect very distant parts of the field? So trying to build a, well, what people would call a very straightforward statistical model actually becomes very non-straightforward as you go through it and as you try to account for more effects. And so what happens is you end up with tons of parameters and you end up with this very, very, very complicated problem of just trying to do something which should be relatively simple, of just taking a couple of fields and smashing them together. So in addition to this sort of averaging approach, there have been a lot of different methods for trying to construct this function f. So just as a reminder, f was the hypothetical map taking our ensemble of fields and turning it into one field that hopefully matches the data. And there's been a lot of methods for doing this. One is the ensemble averaging approaches that I just told you. So the democratic approach where everyone gets equal weight is the preferred because it's very easy to do. But this has a lot of problems, which is namely that because models simulate local variability quite differently from each other, when you average them together, you essentially smooth out all the possible variability. And you end up with something that, if you average the whole field, may look sort of close to the truth. But if you look at any sort of local component of it, it looks nothing like it. It's just a big blurry mess. And that tells you very little. So stepping up in sophistication, they came up with these Bayesian methods, which would try to account for different sources of variability, variability within the model, variability within the parameterizations. These are quite complex, but the sort of innovation over the averaging approaches is that these are going to directly condition on observed fields. And that's nice because you usually end up getting something better, but these are extremely expensive to run. And so often this was only going to be limited if you wanted to look at something like the Arctic or maybe a little zone in the tropics. But trying to run this over the whole globe is essentially impossible. And then there are the regression and machine learning approaches. So I'm not going to go into the details of these, but essentially what these are trying to do is they phrase it sort of as I suggested you should phrase it. which is we have some collection of models and we just want to learn some map to a target. So we can think about this very abstractly as we have this X, it's high dimensional, it's complicated. We have this Y that's high dimensional and complicated. We just want to learn some map from X to Y. So this is actually what we did as well. So this is the work that this is based on a previous paper, which is now published. And there we learned this map with Gaussian process regression. And the idea was very simple. We just used the climate models to predict observational data. And then when we applied in the future, whatever the prediction of that Gaussian process regression was, that would constitute our integration. That would essentially take all that information in the ensemble and give us one field prediction. But there was a big problem. There was a big problem, and this is a problem essentially anytime you work with climate data, and it's almost criminal how much people do not pay attention to this and just naively apply their model. And that's that most of these methods, especially the regression method, and especially my method, are not very robust to this distribution shift problem. So what distribution shift means is that the joint distribution of our covariates, so our models, and our target, the real data, in the training period is not going to be equal to the distribution in the test period. And this is always going to be true for any climate problem. For any climate problem, you only have the Ys available up to the day. And we know there's climate change in the data. We literally know there is some manner of distribution shift happening all the time. You can go read the news and see all about that. So we know this is always going to be a problem, but how much of a problem it is going to depend on the model. If your model is not robust or even invariant to certain degrees of distribution shift, then what's going to happen is your error rates on the train, even if you have out of sample, your error rates are going to be quite different than your test error rates, and usually not in your favor. This is usually going to be in the favor of your test error, which is going to blow up. So even though it looks great on your out of sample prediction, you apply it in the future, the error rates are going to be quite large. Now, of course, there's going to be no way to, there's going to be no way to mitigate this for any sort of arbitrary change. But for small changes, you can have, there are models that are going to be different levels of robustness. And so this, I know no one likes tables, forgive me for this, I'll point it out, but for this actually can have a very significant impact on the predictive skill of your models. So this is a table from our previous paper where we compared a lot of different methods. This is me, and these are all the ones we didn't like. And what this is showing is essentially the predicted error aggregated over a decade. In climate, you always want to aggregate your predictions over sort of a long range period because the individual day-to-day doesn't matter. What matters is the long range trend. So we looked at our aggregated error over 10-year periods, and ours was 1.91 MSE. That number doesn't mean anything, but what it does mean is it was better than LM, weighted ensemble averaging, about as good as these other Gaussian process approaches, and better than a CNN in this delta method. But what happens is, as we go down the line, as we go down from very near-term predictions to very long-term predictions, the error rate is going to steadily increase. Now, we expect this to happen. Of course, as your data moves farther and farther away from the test period, we expect that you are going to have an error rate increasing. So you can see we start from 1.91, and by 2100, we're all the way up here at 2.84, which puts us in line with something like linear regression. So what's the point of your model if it's not beating linear regression? And this also has a very large impact on the uncertainty quantification as well. And this is going to be just as much of a problem, if not more of a problem for climate. Because usually in climate, we don't really, well, you do care somewhat about the sort of predictive accuracy or the bias of your model, but what you're largely caring about is the spread that it's giving you or the sort of predictive distribution. And so here we use something called the continuous rank probability score. This is a very common scoring rule often used in atmospheric science for assessing essentially the quality of a distributional prediction. And so in this case, lower numbers are going to be better. And what we see is, again, we start out low, but by the end, it's quite high. And this is not a fate suffered by all models, however. If you look at something like the ensemble average or the weighted ensemble average, you can see they're actually fairly consistent over time. So it's not something that you are necessarily condemned to if you want to do this problem at all. It's not necessarily a problem with the data, it's a problem with the model. Okay, so what's the deal? Basically, you are always going to expect your prediction error and your predictive distributions to deteriorate the further the test set is from the training set. So, and that could be over time, as was done for temperature, or it could just be in general. We know that if we apply it on data that the model hasn't seen, we know neural networks and other type models are often not going to be very robust to that. So it's not a problem that you can ever really get rid of. There's really no way to make your model completely immune to this distribution shift problem. You can always shift this so that your test distribution is so out there that no model would be able to generalize to that. So we're not really worried about that. That's not a problem. What we can do, though, is we can try to find models that minimize how fast this becomes a problem. So if we take as axiom that all we want to be able to do is at least predict out to 100 years, then what we're going to be looking for are models that grow very slowly in their error rates over these long periods of time. So models that are going to be fairly robust to slow changes from the train to the test. Climate change, thankfully, doesn't happen all at once. There is some manner of progression here. So what we want to find is a model whose error rates increase essentially very slowly over time. And this is going to give us better forecasting skill, because hopefully over the long run, this is going to, instead of blowing up and going, your errors diverging off to infinity, they'll diverge off to infinity eventually, but it'll happen so slow that for all intents and purposes, we're not going to have to care too much. And maybe more importantly, this is going to improve the uncertainty quantification skill by still allowing us to have either our coverage guarantees approximately hold or our CRPS scores be fairly low. So I just want to present a little diagram, and then I'll explain what this means. This is a diagram of basically what our proposal is for handling this and trying to introduce something that is going to be fairly robust to this sort of distribution shifting problem. So what is going to happen is, let's say we start with our ensemble of climate models, and these are all given on their own resolution. They're all sort of just floating out there and given to us as we download them. And then instead of trying to learn this map directly from the climate models to the observed data, or really this is a sort of quasi-observational field. Instead of doing this directly, we're going to do this a little bit indirectly. And one thing that we're going to do is we're going to first downsample this. So we're going to try to reduce the information a little bit. So this is going to incur that resizing bias I told you, but hopefully it's not too big of a deal. And then what's going to happen is these downsample ones are going to be fed through a convolutional neural network. This will give us a low resolution prediction. And then we turn back to our Gaussian process, which is going to upsample it. So in this case, we're taking the sort of, instead of taking the direct approach from this ensemble to the target, we're going to have a downsampling, and then a prediction, and then an upsampler. So let's explain this a little further, and I'll show you this is not true. This is truly not just some ad hoc series of methods that we just tried, but actually does fit together into a coherent framework. So what we're going to do is, instead of thinking of, well, we're still thinking of trying to learn this map from X to Y, but we're going to break this down essentially into 3 stages. And so we're going to essentially treat F as this composition of these 3 different functions, which we can interchange and deal with as necessary. So for downsampling, we're just going to use something simple. So for now, we're just something simple like bicubic interpolation. So something that doesn't need to be trained, but we can just quickly resize models as necessary. For forecasting, we're going to use a convolutional neural network. And then for upsampling, we're going to use this Gaussian process approach. So why are we doing it this way? So the Gaussian process model that we used in our previous paper did not need to go through this. This is a direct approach from the ensemble to the target. And it was very nice because it automatically upscaled the inputs to match the dimension of the output. So one thing I should mention is that the resolution that the models are usually given on is very small, maybe 100 by 200 or so. But the resolution of these observational fields is much higher. It could be around 1,000 by 1,000. And so what was nice is we didn't have to care about resizing. We didn't have to care about any of this. We could simply just take it, feed it in models of whatever dimension, and just let it predict a high resolution field. But it was very sensitive to the distribution shift problem. We know Gaussian processes, as we move away from the test data, as we move away from the training data, are going to tend to revert their prior behavior. And so essentially what happened as we go farther into the future, it reverts to just basically just taking an average of your training data. However, what we found so far, so again, this is ongoing work, is that empirical testing is showing that the CNN was actually relatively robust to the distributional shifts. At least it was robust to shifts that were less than or equal to whatever our data was exhibiting. And so this is actually evident in the first table, which I should probably put back in here, and showed that the error that CNN, while it was overall higher than our Gaussian process approach, it was fairly consistent over time. And so to some degree, we're still figuring out exactly why this works and under what conditions this is going to work. The CNN does appear to mitigate this distributional shift problem. But with a CNN, it usually is going to struggle to sort of upscale your predictions. It's going to have a hard time taking low resolution climate models and giving you a high resolution prediction, unless you have a lot more resource than I do to train something very large. But that was something our GP model excelled at. Even people who are very poor like me can fit a GP model in 30 seconds or less, and it would give you a nice high resolution prediction. My sort of preferred way to look at this, though, is maybe not as just taking F and just breaking it down into 3 components, but actually looking at this as an instance of deep kernel learning. And so this idea was proposed, I believe, in 2015 or so. And so the idea in deep kernel learning was that we would pose a single neural network that, for the initial L layers or so, would have these finite width layers. And then the last, N minus L layers would be infinite width. And so if you're not familiar with the result, there is a result showing that essentially an infinite width neural network is equivalent to a Gaussian process. And in fact, that result was extended in 2017 to show that multiple infinite width layers stacked together also gives you a Gaussian process. And so in fact, our model is exactly this. So our model is starting with our input layer. We first have a downsampling layer or pooling layer. It feeds through a set of finite width layers, and then it feeds through a set of infinite width layers. There's really not much to say on the downsampling. So this is something we're going to look at as maybe something that could be worked on or maybe expanded. But essentially what we're doing is we're just taking each one of these individual climate models as predicted by each one of these groups, downsampling it to a consistent resolution and just stacking it into one little tensor object. And so once we've done that, then each model essentially becomes a channel over which the CNN can operate. For testing purposes, and actually the results I'll show you today, we use a small CNN, which is just 32 by 5 by 32, 32, 32 in one channel. So essentially taking in our initial ensemble and then spitting out a field with just one channel. So essentially just a single field. Some empirical findings here. One, found that mini batching was essential for generalization. So if you try to train this on full batch, it does not generalize nearly as well. This bottlenecking layers are actually incredibly important. Further regularization does not seem to matter much, but may be helpful for getting the average error rate down. So I wrote this initially, and that was true. But actually, I want to say that we've looked at this a little more since I made this slide and found that we could actually just take this CNN and make it much deeper and improve the overall error rates. So that's probably a dead end, is looking at further regularization. And so the way this is going to be trained is essentially we're going to take that stack of 15 models, now treated as channels. We'll call that X prime. And this is going to be used to predict a single channel image, which is just Y hat prime here. And as they do in the original deep kernel learning, this is trained independent. So this is trained independent of the further Gaussian process layers. So the Gaussian process upsampling, we described this a lot more in the paper, but just to give you an idea of what is happening, is we want to define a Gaussian process that's going to map from something that is high dimensional, well, relatively high dimensional, like the prediction of our CNN, to the original data, which is extremely high dimensional. And so the way this worked in that paper and the way it works now is essentially, you can think of this as having a separate Gaussian process model. And this is how the infinite width layers work, because you basically have a separate Gaussian process model that is going to be component-wise in the dimension of the target here. And so what that means is you basically have one Gaussian process that maps this whole field to one pixel, and then another Gaussian process that maps to the next pixel. Then the key is that the kernel functions of those Gaussian processes all share the same parameters, so you only have to learn one parameter set. And then you can just apply it, and simply in just one matrix multiplication, you get your entire field. So we wanted to apply this approach, our deep kernel learning approach. And we're going to look at a data set here where it consists of monthly aggregate 2-meter surface temperature fields as output from 16 different cloud models. So this is a small testing data set. Eventually, it's going to be scaled up to the full 50 models or so in CMIP, now CMIP 6. And essentially, the way this is going to work, in order to validate our predictions into the future, we're going to take one model from this ensemble of 16. We're going to hold it out and use the 15 to predict the 1. And then we're going to repeat that procedure. So essentially, jackknifing out models and getting look at the average error across all of the models, and then also getting some idea of the variability there. And so the idea here, this is a very common technique used in climate science, where you call these perfect model experiments, because we're essentially going to treat one model as if it was the actual climate. We'll train on 1979 to 2015. This is to match the availability of the actual observational data. And then we're going to test on future simulations. And so with future simulations for climate models, it's not just that you can just continue to run the model in the future. You have to make assumptions about how different forcings, like the amount of carbon going into the atmosphere, the amount of carbon being pulled out of the atmosphere, and a lot of other considerations, which are very much policy dependent. And so they've come up with all these different scenarios for how essentially how we're going to mitigate climate change or not mitigate climate change. And SSP 245 here is essentially a medium plausible scenario, which is basically assuming that people continue to mitigate climate change at kind of the rate they're doing. You could probably do better, but you could certainly do a whole lot worse. And so the idea here, though, I mean, one is this is a very common one that people will look at, but also to look at how does this perform under relatively moderate distributional shift. I said this already, but essentially training is going to work in 2 stages, just as it did in the original deep kernel learning work. First, you will train the finite width layers, the CNN, and then you will train your infinite width layers after that, which essentially just amounts to estimating 2 variance parameters. So how we will actually go and evaluate these experiments is, as I said, we will use these perfect model experiments where each one is jackknifed out through. And then we're going to look at 2 different levels of forecasting here. One, we're going to look at the raw sort of CNN forecasting. So how does the low resolution predictions of the CNN compare to the sort of low resolution targets? And then we'll look at the predictions of the high resolution. And so the idea here is to try to separate out what is the CNN doing versus what is our upscaler doing. So I want to show you an example, and this is what gave me a lot of hope. This is an example where we used the NNGP, which was my previous method. That's the blue line here. This is the error rates as plotted over time into the future, of course. And the orange is the error rates as produced by the downsample model. So this is purely for the low resolution prediction. So this is everything just the CNN is doing. If we look over here, we just have a sort of a moving average view so we can get an idea of what the slopes and everything look like. And so what this tells us is actually this CNN is doing exactly what we hoped it would do. Although I still don't totally understand exactly why it's able to. That's something we're looking into. But what it is telling me is that the rate of increase of this error is much, much slower than the Gaussian process. So just the CNN itself has a much slower increasing error rate. Now we notice there's this sort of gap here where the beginning errors of the CNN are higher. That actually is just a function of the fact that that CNN was fairly shallow. So we've done some testing now, and now this line is down here. So it actually ends up being a uniform improvement over it, which is good because the NEGP was mostly a uniform improvement over the previous approaches. So we like progress. If we look at another example, that was just one single model. We look at another single model. It's not always as, well, I mean, it's always better, but it's not always going to be as much of a absolutely does not increase in error over time. Sometimes there is going to be a little bit of a trend here. That's fine. It just means this model probably exhibited a much higher degree of distributional shift. But if we look at the aggregate behavior over all 16 models, we can see that actually the pattern is quite clear. Again, which is that essentially the same story on the first model and the second one I told you, where the error rates increase much more slowly. So now we looked at the upsampled predictions. And in this case, this is now including not just the CNN's prediction, but it's taking the CNN's prediction and upscaling it, and then looking at the error of that on the actual high resolution target. And here we can see now there is a little bit more. So now there is a little bit more. So what this tells us is that while the CNN is able to give us something that is relatively robust to distribution shift, that NNGP or that GP is still making our model a little bit brittle to that. So without more resource to train a very, very fancy upsampler, I'm not sure how much can actually be done by this. But at least if we can get the CNN relatively flat, then the effect of using the upsampler is hopefully not going to be too much, and hopefully it'll at least be less than whatever the previous methods are going to be able to handle. And so now I actually want to get to probably the most important part, but also the part that's still under active development, is that one thing you may be asking is, Trevor, didn't you say that uncertainty quantification was super important? And now you're here telling me that I should use a CNN and some upsampler thing. So in the neural network Gaussian process, we'll get to that. So the neural network Gaussian process, or any sort of GP model, is going to have some sort of inbuilt mechanism for quantifying uncertainty. And often this is the line of attack, or the sort of, not attack, but the line of argument people will use for saying this is why you should use a GP versus a neural network. But unfortunately, in our case, in order to make things scalable and actually work, so in order to actually get it to run, we had to assume that the variance was shared at every single spatial location. So I sort of hinted at this when I talked about predicting the field component-wise and having to share a parameter set. So when it shares a parameter set, we're implicitly saying the variance needs to be the exact same everywhere. And this is an absurd assumption to make for climate data, because we know that the variability in things like mountainous regions is very high. And the variability in tropical ocean areas, it tends to be quite low, at least for temperature. It doesn't change too much if you're near the equator. And so this gave us very severe overestimation of variability in low variability regions and very much underestimated the variability in these high variance regions. And that's bad. That's not good, because essentially this variance is actually somewhat useless thing. It's actually somewhat useless for telling us anything about these sort of predictions at the local level, and that the whole local level was the whole thing we wanted to solve here. It was nice to get good error rates, but without this, it was we moved away from trying to show a lot of the local variance. Now our new approach here. So it was bad enough with the GP model, and now our new approach is going to do downsampling and feed it through a CNN. So this seems pretty hopeless for UQ. And it is fairly hopeless for UQ. So when things are hopeless, we give up and try something else, right? So in this case, we're going to use a completely different technique. We're going to basically just say, all right, forget the GP uncertainty, forget making that neural network Bayesian. That's always very tempting. I've yet to get it to work well. Let's do something else. And so one of my favorite topics recently is conformal inference or conformal prediction, however you may hear. And what this is a framework. It's a very broad framework. It's very well developed these days for constructing exact predictive intervals using finite samples. And the only requirement here is that your train and test data, or really your losses on this, are exchangeable. And in practice, well, we're going to need enough data to sample split. And it turns out we actually do have enough data to sample split. We only have about 800 observations. You think maybe that's not enough to even train the neural network. It turns out actually that is enough observations to not only train the neural network, but train it on a reduced sample and split off and perform this conformal inference. So what this is trying to do is, given some level alpha and given some new input x, then we're going to try to construct this set C alpha x such the probability that y is in this set is greater than 1 minus alpha. And in many cases, actually, I think this should be 2. But in many cases, this is actually going to be very non-conservative procedure as well. So it's not just going to give us some infinitely wide interval here, but it's going to give us something that actually concentrates very quickly on this set is going to concentrate very quickly on the actual alpha level interval. So let's step through essentially how this works, because now there's suddenly a lot on the page. So how do we get this set? How do we estimate this set? Well, essentially what you're going to do is you're going to take your training data, I equals 1 to n, and partition it into 2 sets. One's going to be the new training data set, which is just goes up to m. And then one's going to be your validation set. We'll train our model on dtrain here. And we will look at the residual fields on dval. So we're going to get some idea of what the residual distribution looks like on the out of sample, but hopefully still hasn't changed too much distribution. And so this is going to give us essentially a set of n minus m fields. And what we want to do is we want to find the 1 minus alpha % set of most central fields. So whatever the fields are that are closest to that center of the distribution. So we have some distribution of, I should have put a picture here. We have some distribution of fields. We want to find the ones that are closest to the centroid. And you can do this. There are many techniques for trying to do this. So we are currently working on something, a data depth based technique, which essentially will treat these fields as functions and try to find the set of most central functions. So this can be done. Just take my word that this can be done. And then what we're going to do is we're going to predict every single element in the test set. I didn't list it up here, but the test set is implied to be the future one, by basically just taking our prediction and adding each one of these residual fields. And so this, of course, is going to cost you a lot more in memory to do this, because now we have to store this history of fields. But what it's going to do is it's going to give us this ensemble of predictions automatically. And so what's nice is as long as these residuals in the residuals in the validation set and the test set are exchangeable, which hopefully now that we've reduced this error rate to be fairly flat, it's fairly exchangeable, then this 1 minus alpha % central region that estimated on the validation set will also have 1 minus alpha % coverage on the test set. And I'm not sure, actually, I don't have a plot here, but this is something that we have, well, you can prove it fairly easily, but we've also looked at empirically if the data meets this, and it actually does hold up quite well. But that was done after I made these. So what's nice about this approach is that, one, this is automatically going to give us some spatially varying uncertainty quantification. Because those residual fields, if they don't vary too much in the validation set, then the residual is going to tend to be quite small, because it's going to do a good job predicting there. And for these high variability regions, it's going to have much more spread. So it's automatically going to account for this sort of spatial distribution of the data. If we measure its skill through the CRPS, once again, then we'll see that again, this is fairly flat over time, which is indicating that these distributional predictions are quite good and actually are not decaying too much in skill as we go into the future. Okay, so there's still a lot of work here, but this is what I sort of wanted to show you that we have today. So just in conclusion, distribution shift is very much a fundamental problem in climate science, something that you absolutely have to solve. So you need to consider this before applying any model to future climate data. Some models, like Gaussian processes, will have very strong performance when there's little distribution shift. So we did this in precipitation as well in the original paper. That has relatively smaller distribution shift than temperature. And so the GP actually had really great error rates over the full time series. CNN models are, I say evidently here, more robust to these types of distribution shift that we're experiencing. We're still trying to figure out what exactly and quantify that and characterize that shift. But for this problem, at least the empirical evidence is showing that the CNN is performing quite well. And then more work is still being done to improve these error rates. So actually, right now, we've replaced essentially the CNN with a much deeper residual CNN, which performs quite a bit better. And then finally, we're still working on the results for the UQ as well. Yeah, that's it. So thank you for listening.
Any questions?
So,
have you looked at all at transformer architecture networks for this problem? Something with the spatial tokens.
I have not actually. I'm not opposed to them. I just haven't looked. Is there a reason to believe they would be more robust? Because I'll do it. I mean, I don't care about CNN. Like
my empirical experience is that not to divulge too much about an upcoming work.
I'm not gonna scoop you. Don't worry.
Thanks. I'm not working on climate science, so but in a remote sensing context,
yeah,
using completely like no training data at all, I could get extremely high performance, better than stuff that had some like 80-20 split with a big enough transformer architecture model that could learn sort of.
Oh, I see. Very deep features. Yeah. Well, that's certainly something to look into. So yeah, actually, maybe I should talk to you more about this. So I have not looked at those myself. And if we could avoid training the CNN, like that'd be great. Actually, it doesn't cost that much. It only takes like 2 minutes. But that's still 2 minutes, you know, like that's still like that's time to go get another cup of coffee.
Yeah, I was dealing with like 1.5 billion parameter, huge model, but still fine tuning it only took maybe 50 minutes.
Okay.
On a couple tens of thousands of examples, so it's really not so bad.
That's not. Yeah, it's not. I mean, yeah, for deep learning, that's not bad at all. Okay. Yeah, it's a good idea. Okay.
Like a specific, like you get different results, you know, and the different that you're trying to feed it.
Yeah, so that this part is still, well, let me be honest. The way we came up with the downsampler was we just needed a way to get all the fields into one tensor. So that was sort of the initial push there. This resolution was chosen because this is fairly close to the smallest resolution in the actual models. And so the idea was, all right, let's just try to downsample like as little as possible. And if we do that, then we won't have to upsample too much. So maybe the NNGP will not incur too much of this sort of distribution shift problem. So the hope was to try to mitigate that by making the NNGP work less. We have tried it. So actually we were initially testing this on much smaller fields. So we tried this like 10 by 20s and like 20 by 30s, things like that. The results are not that far off for the low resolution prediction, but for the high resolution, it was a little bit more issue. So actually, that's probably where we need to concentrate the effort more, is like how to get something a little more robust for re-upsampling it. But yeah, so but taking this very low is a good idea. This is something they actually like to do for climate science. Is there's a lot of redundant information in these fields. They're very continuous. There's a lot of redundant information, and so how to work with sort of the compressed climate models is very much an active topic. So if we could get this working just as well on something tiny, then that would be fantastic. I think he was up first then.
So the mapping of the
flow to these sort of Mercator-like projections to store samples.
Mhm.
When you're fitting model-based on sort of this tensor representation,
Yeah,
how well you fit the poles versus how well you fit the equator rural regions doesn't really reflect, you know, your overall error when you look at the sort of topology of the field itself.
yeah.
Is there any concern that is there any quantification under sort of the actual planetary shape versus the rectangular?
Yeah, no, that is a
Like, if you
that's
fit the
important
poles
consideration.
poorly
Yeah,
on this map, that might seem like a very large error, but
Yeah.
when you collapse it back down onto an actual.
Yeah.
The shape there on the spread of the planet, and we're really only a little bit off.
yeah.
It's a
So
small error.
right, no, I mean you're absolutely right. So right now the way that a lot of them will sort of cope with that problem in climate science is you just do this equal area weighting. So we essentially just down weight the errors at the poles a lot, and so that way, because we just account for the fact that like they are representing a much smaller area than those tropical areas are representing.
Are you trying to do the same thing when you're getting, when you're actually training the?
So we've tried it both ways. One where you have this equal area weighting, and one where you don't. It didn't make that much difference. So I've just left that outside. Actually, where I would like to take this is I'm working on another project with a guy where we're using spherical convolutions for this. And so that in that case, we don't have to worry about it too much because we're actually respecting sort of the geometry of the field. So that remains to be seen. I don't know, like if there's an easy implementation of that for this, but yeah, no, it's very good. It's a good point.
So it's a follow-up question for the downside.
Okay.
So I'm just wondering if like so if the robustness model comes from mostly from the downsampler or from CNN, because like downsampling is really something like this.
Yeah. I don't really have an answer for where exactly the robustness is coming from. So we've been trying to look at how do different degrees of downsampling affect the prediction error, which is sort of my best, without some sort of theoretical way of doing this. My best way is just sort of look at a range of these. And like I was saying, like the downsampling, like it does help. Like it does help a little bit, especially because if you try to do something too high resolution, the CNN has a hard time getting you like a high resolution prediction back. Especially if you need to upscale. So the downsampling was helping to a degree, but after you keep downsampling, it doesn't seem to have much more. It seems to start making it actually worse. So unfortunately, I don't have a good answer for you, but that's something we have to look into so the reviewers don't ask me the same thing.
What is the optimum size of the layer? Out of the layer, how should the layer size?
That is a great question. There might be some theoretical results on how you need to bottleneck the information there. I'm not really sure. There's probably a lot of ways you could do it, and probably a lot of choices you could make and get very much the same results. So I'm not sure that there is an identifiable like set of layer or channel widths here. In this case, we just went with 5. Well, basically because 1, 2, 3, 4 didn't work, so we went up to 5, and then that seemed to work. But if you go beyond that, then it starts sort of trying to overfit it a little bit. This is somewhat mitigated because now I have a residual version, and in there we have. I think we tried it with no bottlenecking the residual version. It was a little bit better, but yeah, why or how exactly that's chosen is a total mystery in this case. But I guess that's like a lot of times choosing architectures for deep neural networks. It's just the one you choose is the one that you worked really well on your test and you didn't want to test more.
Any more questions? Thank you very much again.
Thank you.
Rob, any pieces of the blood, and thank you, Dr. Harris.
Really good. Yeah. Actually, we talking to you about this project.